Hello, everyone. My name is Xueyue Zhang, and I'm a PhD student in Professor Oskar Painter's group at CalTech. So today I'm really happy to share with you my research to let the qubits communicate more efficiently with each other. And I'll also talk about my journey towards the quantum world. So the first question is always, why quantum? So physics has been my favorite subject ever since I studied it in middle school. And I loved it so much that I participated in the Physics Olympics in high school. And there I saw many different experiments. And among them, the colorful optical experiment really attracted me. And that's why I made photonics as my research topics for my undergrad. But the sparking moment for me is really during the campus visit for grad school. And there I saw many different labs doing quantum photonics. And that's when a whole new world is opening up for me. It's not just fascinating, but also helps to answer the question that I had long about the applications of quantum mechanics. So people have unlocked different sets of physics laws to change the world. If you think about it, the things we use every day, like engines, power system, and internet, they are all lived on the foundation of classical mechanics, thermodynamics, or electromagnetics. But what about quantum mechanics? It's such an exciting idea to help unleash the power of quantum mechanics into our everyday life. And I want to be part of it. That is the trigger for me to enter the quantum world. And the holy grail of my PhD research is to do quantum simulation. And I believe no one can motivate it better than Professor Feynman. He said, nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. As he said, the goal is to study nature. So it is a science. It includes physics or chemistry or some other things. But we need to build a device in order to achieve this goal. And it's not an easy problem. It involves a lot of engineering. And my research as an experimentalist lies exactly at the intersection between science and engineering. In the past few decades, people have seen great progress in different physical platforms. For example, trapped ions, neutral atoms, and superconducting circuits. And among them, my personal favorite is superconducting circuits. It has great controllability and readout over individual qubits. I believe in your course you have learned about the qubit, and here is what it looks like physically in my group. So this rectangular thing together with the tip is a qubit. And you also learned to implement the gates as the matrices in your class. So in my group, we put the microwave lines adjacent to the qubits in order to implement those gates.
Sorry to
You also learn.
Oh,
yeah.
Sorry to interrupt. Maybe if you want to expand to the use slideshow, I think we can see your notes.
Oh, sorry
about that. No worries.
Okay, let me see. Is this the right screen that you're looking at?
Yeah, that's perfect.
Okay, cool. Oh, sorry. Yeah.
No worries.
Right. So you also learned about the principles of measurement. And here we put the LC resonator close to the qubit. And if we probe the state of the LC resonator, we can learn about the state of the qubit. And now that we have a qubit that has full controllability, we can put many of them together to build a quantum processor. This is an example from IBM Quantum, and I believe by using Qiskit, you're controlling some smaller version of a quantum processor. And yeah, here you can see a qubit can talk to its neighbors, 2 or 3 qubits. But what if a qubit can talk to other qubits that are farther apart? In that way, we have a much higher connectivity and it has a lot more applications. In order to do that, we also get the help from light, as Donnie said before. So here in my group, we put the microwave waveguide close to a bunch of different qubits, and the microwave photons in this waveguide can mediate interactions between qubits that are far away. It is really like building a telephone line among those qubits. And 2 years ago, we have realized this idea by building a transmission line waveguide coupled to 7 different qubits here. And currently, I'm working on a project that involves a more complicated waveguide that gives us more degrees of freedom for engineering, and we can use it to realize different simulation problems. Here we also have like 10 qubits coupled to this waveguide with full controllability. And this controllability also gives us a hard time to wire up the fridge, so it looks a little messy here. And the direct application of this project is to do quantum simulation for many-body problems. So in nature, the interaction between particles is usually beyond the nearest neighbor. For example, the Coulomb interaction between electrons falls as power law. And our system, having the ability to have interactions beyond nearest neighbors, is a more natural platform to simulate those kind of questions. And in the longer term, it can also be a novel architecture for quantum computing because it offers high connectivity gate set, and potentially it can be used to save a lot of overhead for doing fault-tolerant quantum computing or error correction. And behind the scene of my research, a typical project usually consists of 5 different steps. So first, we want to identify the problem we want to study or simulate. And from that, we have the parameters at hand as our design goals. So we do a lot of microwave simulation to have the layout of the chip. Once we have that, we will go to the clean room. You can see that's me in the clean room doing fabricate the device. And we cool the device down in the dilution refrigerator that can go down to tens of millikelvin. And we also play with room temperature electronics to do the measurement. But most of the time, I just write the scripts, like you control the IBM processors with Qiskit. I also have my script to talk to my device. And lastly, we do the analysis. So looking back at my quantum journey, if there's one piece of advice that I want to give you, that is, be confident. I didn't know anything about quantum computing except for a very basic quantum mechanics class before grad school. And I couldn't have imagined I'm making my own 12-qubit device now. When I faced obstacles along the way, believing in myself is the force that led me through. It's not easy to master things in this mysterious yet fascinating quantum world. But for the entire community, it's a daunting task to do fault-tolerant quantum simulation or computation. But be confident. Don't set the limitation for yourself. Just go step by step and qubit by qubit. When we look back, we can see that we have already gone pretty far. And that's what I want to share with you today. And I'm happy to take questions you might have.